Hello, welcome to AP Calculus, Chapter 2, Lecture 1. And this is Part 1. There's no homework that goes with this lecture, but it's a very important theoretical lecture. So you might not completely understand everything when you finish watching this video, but I want you to take all the notes. And as time goes on in chapter 2, I think it'll start to make sense. So what we're going to go back to is the biker situation, the bicycle situation that we had in chapter 1. And we had a bicycle and on a 30-mile journey. And at the 20-mile mark, there's a 20 mile per hour sign. And it took an hour and a half for the biker to make the whole 30 miles. But the question is, how fast is the biker going at the 20 mile an hour sign? This was the first question of calculus. How do you get an instantaneous speed or rate of change at that 20 miles an hour sign? So once you go ahead and draw this out, pause the video if you need to. Now, we're going to assign to the motion of this biker a mathematical function. So let's say that we were able to plot the biker speeds up and slows down with, say, a satellite, okay? And we're able to take a lot of measurements, and what we came up with is that the biker rides, the position of the biker is 40/3 times the time squared. So we were able to mathematically model the biker's movement. And that's the equation we got. So we're going to graph it. So that's a parabola. And the position would be on our y-axis. And time is on our x-axis. So let's draw a parabola, draw a real wide parabola like that. And at 30 miles, the time is 1.5 hours. Now, I got a time of 1.2247449 for 20. How did I get that? Well, I just set the position, 20 miles, is equal to 40/3 times t squared, and solved for t. Okay, so if you solve for t, and it goes on forever, but I just truncated it after 7 decimal places, and so that's where we got that. It took 1.2247449 hours to get to that point. Okay, so go ahead, pause the video, and draw this graph, and then come back. Okay, so what we want to do is get the rate. And we know that distance equals rate times time, right? So if we want to get the rate, that means the rate is equal to distance over time. But it's really not just distance over time. It's actually the rate of the bicycle is the change in distance over the change in time. Okay, so that is just a slope. Change in distance over change. Remember, distance is y, time is x, so it's just the slope, which we a lot of times call m, right, in math class. And it's the change in y over the change in x. So that's y2 minus y1 over x2 minus x1. So to get the rate for the whole journey, it's going to be 30 miles, y2, right, 30 miles, minus 0 miles over 1.5 hours minus 0 hours. Okay, and you would get 20 miles per hour. That is your average rate. Average rate of change. So really, that's all we're talking about when we're talking about speed. So the biker averaged 20 miles an hour. That doesn't mean that he was going 20 miles an hour at the sign. That was just the average rate of change. Now, we can graph that, put that average rate of change on the graph, and you may want some colored pencils for this part, but that is just a straight line, right, with a slope of 20. This is called the secant line. The secant line is the average rate of change, all right? So it's just a straight line there. Y2 is 30, Y1 is 0. X2 is 1.5, X1 is 0. Okay, so we get that. So let's go ahead and define secant line here. A secant line, this is important for the test, is just a line that pierces a curve in two places. Okay, so that's it's just a straight line. Very important in calculus. So we've got the 20 mile per hour as the rate of change for the whole thing, but how about we sneak in, this is what we're interested in, what's the rate of change at 20? Okay, the exact rate of change. Well, we could get an estimate of that by picking a point really close to this 1.2247449. How about we pick something really close to that? Let's pick 1.23 hours. Okay, so we need to get the y value at 1.23. So P of 1.23 is 40 over 3 times 1.23 all squared. All right, and that is 20.172 miles. Now that's not super close. It's 0.17 miles away from the 20 miles an hour sign, but it's a lot closer than 0 or the 30 mile mark. So let's get the average rate of change between those two closer points. Okay, so the rate, which is the change in distance over the change in time, would be, change in distance is 20.172, that's miles, minus 20, so that's our 2 points. 20.172 would be up here, minus 20 over 1.23 hours. So the top is miles, the bottom is hours, minus 1.2247449. So that's 32.73 miles per hour. That's a much better estimate than picking 30 and 0, which gives us 20 miles an hour. That's a much better estimate because our points are really close, much closer to the sign. Okay, so I'm gonna give you some definitions. We're gonna leave this up here for a second, give you some definitions, and then we're gonna pick an even closer point. Okay, some really important points for calculus. The average rate of change between 2 points is equal to the slope of the line connecting the 2 points. So average rate of change, slope of the line. So that means this blue line has a slope of 20. Okay, and that gives you the average rate of change between 0 and 1.5 hours. Okay, so the average rate is equal to the slope of the secant line. All right. So what we're going to do, let's see if I can do this work up here. We're going to pick a point even closer to the sign. Okay, so 1.23 is not close enough. All right, how about we pick 1.2248? That's really close to 1.2247449. It's just, you know, it has the first, let's see, 1.224, yeah. So we're getting into the 10,000ths place here. See, I see why I'm confused. I put an extra 2, 1.2248. Okay, we're getting into our difference all the way to the 10,000th place. So that's pretty close. So first of all, P, what's our position then? What's our mileage at 1.2248? That's going to be 40 over 3 times 1.22. I'm trying to write without smudging all this. It's not that easy. Squared. All right, you put that in your calculator to get 20.0018 miles. Okay, so now that's really close to 20 where the sign is. We're only 0.0018 miles off. Okay, so let's get the rate then. Rate is change in distance over change in time. So that's going to be change in distance 20.0018 minus 20. So we're in miles on top, over 1.2248 minus 1.2247449 hours on bottom. Okay, that is 32.73 miles an hour. So far, that's our best estimate of how fast the biker was going at the 20-mile-an-hour sign. It's not exact, but that's our best estimate. Okay, I'm going to leave that up there, erase this, and write a little bit more down about. So I'm going to introduce you to another line that is super important in calculus. So we represent an instantaneous rate. That's the question here. How fast is the biker going at 20 miles an hour at the 20-mile-an-hour sign? We want the instantaneous rate. We can represent that graphically by a tangent line. Okay, different from the trigonometric tangent, okay? So a tangent line touches but does not intersect the curve. It just grazes it. So a tangent line, instantaneous rate of change. So I'm going to do this one in red. So the tangent line to this curve, this parabola at 20 miles and 1.2247449 hours would look like this. So see how it grazes there at that point but doesn't intersect. That's the tangent line. What we want to get is the slope of that line. If we can get the slope of that tangent line, that's the speed that biker was going exactly at the 20-mile-an-hour sign. It's honestly crazy amazing. Now, let's look at these two numbers here. I'm going to put this up here. We'll put it down here. So I didn't show what these numbers were, but on top it's 0.0018, right? 20.0018 minus 20. And these two numbers, when you subtract, are 0.0001. That is almost something that we talked about in chapter 1 all the time. What form is that really close to? 0/0 form. Okay. So you keep, I'm going to erase this. You keep going down on your notes. So how could you compute the exact, let's go exact, we don't really need that, but it helps, instantaneous velocity? All right, what did we do in chapter 1? We took the limit. So what we're going to do is, if the rate is the change in distance over the change in time, we're going to take the limit as change in time approaches 0. Because how long did it take that bike to pass that 20-mile-an-hour sign instantaneously? Well, it's 20 minus 20, right? Are the hours 1.2247449 minus 1.22449. You know, it's the exact same time. So the change in time was 0. So delta D over delta T. And we end up, what's the change in distance? 20 minus 20. The change in distance is 0. The change in time is 0. So we have 0/0 form. And that needs more work. It's indeterminate form. So I'm going to show you how to do that work and get an answer. Okay, I'm about to erase this whole board, so pause it if you need to. Okay, let's draw this again. Draw the graph again, not the biker. So we've got time, position. In fact, I drew this too close to the left side of my board, so give yourself a little space on your notes. If you need to erase, I'm sorry about that. So I'm gonna do, we're gonna do a parabola here. Do a nice, gently sloping upward parabola. Let's call this the 20-mile-an-hour mark right here. So we're not doing the whole thing here. Now that number, that 1.2247449, and it's actually the square root of 6 over 2. So that's what I want to do that in radical form instead of decimal form. Now what we want to do is pick a point that is close to root 6 over 2. And we're going to call that point root 6 over 2 plus delta t. And delta t is just a small change in time. And when I say small, it's kind of like that 0.0001 that we picked earlier. Something tiny. Think a billionth, a trillionth, okay, of an hour. But I can't put it that close together. You wouldn't be able to see it. And then the y value would be p of root 6 over 2 plus delta t. Okay. So this, of course, is at 20 miles. And this is just a little over 20 miles. So we know that the rate is equal to the change in distance over the change in time. The change in distance is p of root 6 over 2 plus delta t. All right, that right there, minus 20 over root 6 over 2 plus delta t minus root 6 over 2. So that minus that. Okay, so that's p of root 6 over 2 plus delta t minus 20. That's going to just be a little bit over 20. And then the root 6 over 2 and negative root 6 over 2 cancel out, and you have delta t. So to find the instantaneous rate we're going to take the limit as delta t approaches 0, as the change in time approaches 0. That's what instantaneous means. Okay, so now we're going to actually do a little math here. So I'm going to erase all this. So we're going to take the limit as delta t approaches 0 of p of root 6 over 2 plus delta t minus 20 over delta t. Now let me remind you that p of t is equal to 40 over 3 times t squared. Okay, so p of, what we're going to do is plug in root 6 over 2 plus delta t in for t. So that's the limit as delta t approaches 0. This is our kind of our x, like if it was p of x or p of t, this is our t. So it's 40 over 3 times root 6 over 2 plus delta t. And we've got to square it because t is squared. Minus 20 over delta t. Now I'm going to take that and FOIL it out because we're squaring that, right? So that's just root 6 over 2 plus delta t times root 6 over 2 plus delta t. FOIL that out. Root 6 over 2 times root 6 over 2 is going to be 6 over 4. All right, and then we're going to have root 6 over 2 times delta t plus another root 6 over 2 times delta t. That's 2 times root 6 over 2 times delta t. It's just 2 of them. You double it. And then delta t times delta t would be plus delta t all squared. All of that is times 40 over 3, right? Minus 20. So I FOILed it out. That's just this part FOILed out. Times 40 over 3. And then minus 20. Now let's distribute the 40 over 3. So 40 over 3 times 6 over 4 is just 20. Okay, so we have the limit as delta t approaches 0. Okay, you can put that in your calculator. 40 times 6 over 3 times 4. That's 20. Plus, if you do 40 over 3 times, that's going to be 40 times root 6 over 3, right? Because the 2 over 2 cancels. So 40 times root 6 over 3 times delta t. Can't forget that. And then we have 40 over 3 times delta t all squared minus 20 over delta t. Well, something fortuitous happens. The terms that don't have delta t in it cancel out. We're going to have the limit as delta t approaches 0 of 40 root 6 over 3 times delta t plus 40 over 3 times delta t all squared over delta t. Now what can we do to the top? We could factor out a delta t and then cancel out the delta t and get rid of that 0 on the bottom. So if we factor out a delta t, I would have delta t, so the limit, sorry about that, as delta t approaches 0, we'd have a delta t times 40 root 6 over 3 plus 40 over 3 delta t. Because I factor out a delta t out of this delta t squared, there still leaves a delta t over delta t. As we can cancel that out as long as delta t does not equal 0. So finally I can plug in the limit as delta t approaches 0 of 40 root 6 over 3 plus 40 over 3 delta t. Plug in a 0 right there. And the answer is 40 root 6 over 3. Okay, well let's see what that is. 40 times the square root of 6, that's 6 to the 0.5 power, divided by 3 is 32.66 miles an hour. Well, what was our most recent estimate was 32.73, I believe. This is the actual answer. That's the instantaneous rate of change at the sign. All right, calculus allowed us to figure that out. You can't do that with algebra. So pretty incredible. All right, now that, I picked that example on purpose because it's, having to deal with all those delta t's and everything, and it's kind of a pain in the butt mathematically with these radicals and everything. Things do get easier, but I wanted to pick my initial one to be just a little bit hard on purpose. So don't worry about it. Things are going to make sense as we go along. So this is, we're going to do the last little bit of our lecture as the definition of the derivative. Because what we just did was take the derivative, which is what chapter 2 is about. Okay, so I'm going to just draw a nice little pretty function here. This one I don't have to worry about. Let's just make it a nice curve like that. Okay. So this is x, and this is the y, which we call f of x. And let's say this point here is f of x. Let me get that out of the way. And let's say that this point here is x. And then we're going to pick a small amount of change, x plus delta x, where delta x is small change. Okay, so so this value right here, where it crosses the y-axis, is f of x plus delta x. So instead of using t's, we're using x's because it's not always time we're trying to figure out. All right, this is f of x. So the question is, what is the instantaneous rate of change at x? The average rate is equal to the slope of the secant line. All right, that is an important concept that we'll use quite a bit, but that's not what the question is asking. The instantaneous rate is equal to the slope of the tangent line. Okay, let's draw the tangent line in there. So do that in red. That'd be something like this. So we're looking at a slope of that line. Okay, to get that, here's the formula that you use. You take the limit, and we just did it, as delta x approaches 0 of the change in y, f of x plus delta x minus f of x. So this is y2, and this is y1. y2 minus y1 over the change in x, x plus delta x minus x. Okay, that's x2, and that's x1, x2, x1. Okay, so the x's cancel out, and you get the limit as delta x approaches 0 of f of x plus delta x minus f of x over, and again, your x's cancel here, delta x. That is the definition of the derivative. So the formal, I'm going to write it again, definition of the derivative, which is just an instantaneous rate of change, is, now this, what we call the derivative, we call it f prime of x. And it's the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Okay, and again, this is called, that little dash there is prime. So the derivative is f prime of x. What's the derivative of f of x? It's f prime of x. And f prime of x, this answers the first question of calculus. So if you'll go back to day one, all right, we talked about the two questions of calculus. This answers the first question. It's take the derivative, and you get an instantaneous rate of change, which is the slope. All f prime of x is the slope of the tangent line. In fact, I'm gonna have you write that down. We'll do it in red since I drew the tangent line in red. F prime of x is equal to the slope of the tangent line at x. That does it for this lecture. There is no homework attached to this. We will be doing math problems starting with tomorrow's lecture, and I'll call that lecture 2.1a part 2. Okay, so I know this was a long lecture. If I know you may want to watch this one twice if you have the time to do it. Maybe after you take the notes, then watch it through without taking notes, and it may make a little more sense. All right, talk to you next lecture.